Hello everyone, welcome to Samadhan Life Science. In today's video, we will learn about molecular orbital theory and how to predict bond order and magnetism using that theory but without drawing the actual diagram. Now, why do we need this theory? Because before that, we had valence bond theory, which was much easier to explain the bonding in molecules. But VBT could not explain some properties like paramagnetism in oxygen molecule or the fraction bond orders. Now, according to molecular orbital theory, when two atomic orbitals from two different atoms comes together to form a molecule, for example, here we have two hydrogen atomic orbitals, those are 1s and have one electron in each orbital. So when they approach each other, there is a disturbance in electron and nucleus in the atoms, and they form two new orbitals with different energy than the original atomic orbitals. One is lower energy, which is called bonding orbital. Another is higher in energy, which is called antibonding orbital. And these two new orbitals are called molecular orbitals. Okay. Now these orbitals were formed from two 1s orbitals. So this bonding orbital is 1s, and we will name this antibonding with a star. Okay. Now these bonding orbitals have lower energy and the antibondings have higher energy. So more electron in bonding orbital means a stable molecule. Now this is a diagram for molecular orbital. Here are the atomic orbitals and in the middle are the newly formed molecular orbitals. Now let's see the arrangement according to energy. So 1s star, then 2s, 2s star, then pi 2px, pi 2py, those have same energy, and then sigma, then pi star, antibonding star, and then sigma star antibonding. So when the number of electron, total electron, is less than equal to 14, this is the molecular this is the electronic configuration, and every molecular orbital can has two at the most electron, and the energy is lower from high to higher in this direction. So we will feel the electron also in this direction starting from the here. Okay, but if the number of electron is greater than 14, then the first part will remain the same, but this sigma 2pz comes forward, and then pi, and the last part is again same, star, and this antibonding. Okay, so here only interchange position between these two. You need to remember these two sequence to put the electrons. Okay, you don't need to remember diagram like this. So this sigma and pi comes from the overlap. So if there is a head-on overlap between s or p orbitals, then the orbitals we call sigma, and if there is sidewise overlap in p orbitals, then pi orbital. Now let's solve this question from this year question paper. So they are asking the occupied molecular orbitals of carbon monoxide. So carbon has 6 electron, oxygen has 8, so total 14 electron. So sigma 1s star, 2s star, then pi 2p, and sigma 2p. So 2, 4, 6, 8, 10, 12, 14 electron total. Now let's see the option. So in first option there is head-on overlap of two s orbitals. So this is a sigma orbital, but the electron density is continuous from carbon to oxygen. There is no gap or node. So this is a bonding orbital, sigma bonding orbital. Now B and C look similar, but in B the electron density is continuous. Why? Because if we suppose name them as positive, then the positive sides are in same direction, the phases are in same direction, so there is no node or gap. The electron density is continuous, but this is a sidewise overlap of p orbitals, so this is a pi bonding orbital. Now in C, these phases are in opposite direction. So there should be one node, that means there should be one region in the middle where we could not find any electron density. So this is a pi but anti-bonding orbital. Now in option D, this is again a sigma orbital because of head-on overlap and the phases are in same direction. So this is again sigma bonding orbital. So now see in the electronic configuration, there is electron in both sigma and pi bonding orbitals. So A, B and D are our correct answer. But there is no electron in anti-bonding pi orbital. So we can exclude C. Now let's solve the bond order, which is the most common appearing question in your GATE exam. So to calculate the bond order, we have to calculate number of electron in bonding orbital minus number of electron in anti-bonding orbital divided by 2. So in the original species, in the neutral species, the atomic number is 7, total number of electron is 14. So star 2 star pi and sigma. So 2, 4, 6, 8, 10, 12, 14. Right? So now the bond order would be number of electron in bonding orbital 2, 4, 6, 8, 10 minus number of electron in bonding orbital this and this. So 4, 3. So we already know that there is triple bond in nitrogen, right? Nitrogen molecule. Now in question we have in 2 minus, so 2 extra electrons. So this part remains the same. We only add the next molecular orbital, which are anti-bonding pi orbitals, and 2 extra electron goes here 1 and here 1. So bond order for N2 2 minus would be number of electrons in bonding orbital remains same, but in anti-bonding 2 extra electrons, so 6 divided by 2, so 2. So the correct answer is A. Now if the bond order is higher, then the bond is more stronger, the bond energy is larger, but the bond length is shorter, right? Now for the magnetic property, if there is any unpaired electron, for example here, then the molecule is paramagnetic. It doesn't matter if the unpaired electron in bonding or anti-bonding orbital, presence of unpaired electron means paramagnetic, and nitrogen into 2 minus is paramagnetic. But if there is no unpaired electron and all the electrons are paired like in nitrogen, then the molecule is diamagnetic. So I hope you now understood how to calculate the bond order using a MOT, and thank you for watching. See you in the next video. Bye bye.